Hello students, this is POTDAR. Welcome to my channel JP Physics. In this lecture, we are going to start our first chapter from 12th Physics, Maharashtra State Board, that is Rotational Dynamics. In this chapter, we are going to study two types of motion, that is circular motion and rotational motion. Both these are types of angular motion. Already in previous standard, you have studied rectilinear motion in detail, that is motion in a straight line. In this you have studied all the terms related to the rectilinear motion, three equations of motion, that is v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as. Analogous to this, in this chapter we are going to study what is the circular motion, what are the equations of motion in circular motion, and also rotational motion. So first we are going to study, or we are going to discuss about the relation between linear motion and angular motion. What are the terms which are analogous to linear motion in circular motion? First we are going to discuss this, and then we go through detail about circular motion. Okay. Now, if I consider one particle is making a circular motion about a circular path which having the radius r. See, if I consider circular motion of a particle, O is the center, A is the initial position of the particle. If after some time t, it comes at position B, this circular path having radius r, and this particle making some angle theta at the center of the circular path, then this theta is called as a angular displacement. This theta is nothing but the angular displacement. Angular displacement. See, in rectilinear motion, you have seen displacement, linear displacement, and the notation for that it was s. In angular motion, the angular displacement, it is denoted by theta, and its unit is radian. Unit is radian. That is angular displacement, and unit is radian. Now, you know the relation between theta r and this arc AB. In time t, particle covers the linear displacement AB. Linear displacement. If I, here the theta is somewhat big, but if I consider a small angle theta, then this distance is look like a linear displacement. So this linear displacement, I can write this AB as a linear displacement, arc AB as a linear displacement, yes. So what is the relation between this r theta and arc AB? You have already studied what is that relation. See, theta is equal to arc upon radius. Theta is equal to arc upon radius. What is this arc? Arc is nothing but AB, and radius it is r. So I denote this AB as a linear displacement, yes, and radius r. Therefore, S is equal to r theta. See, this is the relation between linear displacement and angular displacement. Linear displacement, yes, and angular displacement, theta. Now, if I differentiate this linear displacement with respect to time, we know displacement upon time, it is the velocity. Rate of change of displacement, it is velocity, correct? So ds by dt, it is velocity. If I differentiate this with respect to time, then ds by dt, r is constant, take it out. Therefore, d theta by dt, rate of change of angular displacement, and it is what? Rate of change of linear displacement. What is rate of change of linear displacement? It is linear velocity v. Similarly, what is rate of change of angular displacement here? It is omega. Don't say w. It is omega. Rate of change of angular displacement, it is called as a angular velocity, that is omega. Rate of change of linear displacement, it is linear velocity v. Rate of change of angular displacement, it is angular velocity omega. So v is equal to r omega. This is the relation between linear velocity and angular velocity. Now what will be the unit of angular velocity? Unit of angular velocity. Angular velocity. What is that unit? That unit will be, see, omega is nothing but angular displacement upon time. Angular displacement, it is radian. Angular displacement, it is radian. Then radian upon second, that is unit of angular velocity will be radian per second. Radian per second. Now, if I again differentiate this equation, V is equal to R omega, then what will happen? Rate of change of velocity. See, rate of change of displacement, rate of change of velocity, you have already seen in 11th standard. Okay, so rate of change of velocity, that is dV by dt. Rate of change of velocity means change in velocity upon change in time. That is equal to R, it is constant. Therefore, d omega by dt. That is rate of change of angular velocity. Rate of change of linear velocity, it is linear acceleration. That is A. What is rate of change of angular velocity then? It will be angular acceleration. That is R alpha. Angular acceleration, it is denoted by alpha. Linear acceleration A, angular acceleration alpha. A is equal to R alpha. Therefore, linear acceleration and angular acceleration having the relation A is equal to R alpha. Then what will be the unit of alpha? Unit of alpha, that is angular acceleration, that will be radian per second square. Radian per second square. See, unit of omega, it is radian per second. Again divided by time, that is radian per second, that is radian per second square. So you have to know all this analogy between linear and angular motion. It is angular displacement theta, unit is radian. Formula, it is S is equal to R theta, or you can say arc upon radius. Next, it is angular velocity omega, relation between linear and angular, it is V is equal to R omega. What is the unit of omega? It is radian per second, that is angular velocity. Next, it is, if we differentiate again velocity with respect to time, then dV by dt is equal to R d omega by dt. Rate of change of velocity, it is a linear acceleration. Rate of change of angular velocity, it is angular acceleration. What is the unit of angular acceleration? It is radian per second square. Radian per second upon second, that is radian per second square. Now, we know the three equations of motion in linear motion, that is V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. Initial linear velocity, final linear velocity, linear displacement, linear acceleration. Now we are going to write all the equations in case of angular motion, that is circular motion. In place of V, that is final linear velocity, final angular velocity will be omega. Linear velocity initial, what was that? It is U. We are going to use the angular linear initial angular velocity with omega naught. So what will be the equation? That will be omega is equal to omega naught plus alpha t. See, and linear acceleration, here there will be angular acceleration, alpha, angular acceleration. Omega is equal to omega naught plus alpha t. Now, in place of this second equation of motion, this is linear displacement. Here there will be angular displacement. What is angular displacement? It is theta. So, what will be the equation? Theta is equal to, in place of u, there will be omega naught. Time will be as it is plus 1/2 alpha t square. In place of linear acceleration, there will be angular acceleration, that is alpha. Now, third equation, that will be omega square is equal to omega naught square plus 2 alpha theta. In place of S, there will be theta. So, these are the three equations can be used in circular motion, that is angular motion. These are the three equations in case of linear motion. These are the three equations in case of angular motion. All these basic terms you have to know before going through circular motion, because when we are going to make the derivations, you have to know the relation between linear motion and the angular motion. So hope you are going to understand all these things. Thank you.